So it is my pleasure to introduce Luka Boc Thaler, who is from the University of Ljubljana, who will talk about the geometry of simply connected wandering domains.
Okay, thank you very much, organizers, for the invitation to give me the opportunity to present some of my work. I must say that I'm a bit lucky that now we have this conference online, because 2 weeks ago I was positive on the test, so I wouldn't be able to travel. So that's good. I mean, all fine now. Okay, so the title of the talk, as you can read, is on geometry of simply connected wandering domains. So let's just start with some basic introduction. So we will consider a dynamical system given by the iterates of entire function, which is not linear. So the Fatou set is defined as usual, the set of all points, such that a point is in the Fatou set if it has a neighborhood on which the family of iterates is a normal family. And then a Fatou component is a connected component of the Fatou set. Then another notion that we're going to use, a Fatou component is called pre-periodic if its forward orbit self-intersects. And if it's not pre-periodic, then we call it a wandering domain. Okay. And one of the main goals in complex dynamics is to obtain a complete classification of all possible Fatou components in the given class of maps in terms of their dynamical behavior and in terms of their geometry. Okay, so okay, so for entire function, we have a complete classification of pre-periodic Fatou components, which goes back essentially to work of Fatou, and some special examples were then produced by Ziegel and Baker to sort of close this classification. And and I think it was in yesterday's talk by Anna Miriam Benini, she, I think, gave a sort of a picture what's the classification of invariant Fatou components. I think that was yesterday. And so in case of wandering domains, let's say we have several different types of wandering domains. Topologically, you can have multiply connected or simply connected. And again, we have a complete description of dynamics inside of multiply connected wandering domains. This was done by Bergweiler, Rippon, and Stellat, and this was also talked on Monday morning in the mini course. So we have heard already about this. Then we also have a complete description of dynamics inside simply connected wandering domains in terms of the hyperbolic distance between the orbits of points and in terms of the convergence towards the boundary. And not sure, I think it was said something about this also on Monday of the reduced talk. Maybe I'm wrong. Anyhow, so each of these, so in this specification of simply connected wandering domains, so in terms of hyperbolic distance, in terms of Euclidean distance towards the boundary, each of these cases, in each of these things, you have 3 possible cases. So in total, you have 9 possibilities, right? And it was shown by Benini, Abdou, Figuela, Ribbon, and Stellat that all 9 cases can be realized by escaping wandering domains. And a year later, it was shown that only 6 of these types can be realized by oscillating wandering domains. Okay, so what do you mean by escaping and oscillating? Just to give you a quick sort of view. Escaping wandering domain. So if you sort of look at it from the outside, its orbit leaves every compact set. I mean, the orbit of every point leaves every compact set eventually. Oscillating is the wandering domain, is the domain that in which you can take a subsequence. There exists a subsequence of iterates where the orbit leaves every complex set, and there's another subsequence which the orbit converges to some finite value. And there's a dynamically bounded wandering domain. So the orbit of the domain basically stays bounded, or orbit of points in this domain. Okay, so we know that there are many examples of first two types of domain, and there is a big open question in complex dynamics if there exists an entire function with a dynamically bounded wandering domain. Okay, so I will not talk about the dynamics anymore, but I will sort of try to focus more on geometry of simply connected wandering domains. Okay, and maybe just let me present the result, which I will like to talk about, is the following. So let omega be a bounded, simply connected, regular open set, whose closure has a connected complement. Then there exists an entire function for which omega is an escaping or oscillating wandering domain, and the iterates on omega are univalent. So let's just simply recall what regular means. If you don't know, so the open set is called regular if and only if it coincides with the interior of its closure. And notice that these conditions together, so connected regular open set whose closure has a connected component, implies that the domain is simply connected. Okay. And as a direct corollary of this is that every simply connected Jordan domain is a wandering domain of some entire function. So imagine drawing any kind of Jordan curve in the complex plane. The bounded component can be made precisely that bound component is a Fatou component, is a wandering Fatou component of some entire function.
Is it a necessary condition? Is every wandering
We'll
domain
get to that.
regular?
We're gonna go there. Okay. So thank you, Adam. About these conditions, right? There's another question whether these conditions are also necessary or not, and we'll see that yes, the condition that omega is regular is not only sufficient but also necessary. To see this, recall that if you have a wandering domain, then Fatou set is going to be necessarily disconnected. So you have many components. Then since your map F is continuous and open, which since it's a homomorphic entire function, then the Fn, so the nth iterate of the interior of the closure of your domain, is going to be contained inside the interior of the closure of some Fatou component. Okay. Now, assume that omega is not, the Fatou component is not regular, then we know that if you take the closure and you take the interior, it has to meet a Drea set. But then if this happens, then we know that its forward images cover everything, so the whole plane except maybe one point. Okay, but now this is a contradiction, since this set, so the forward images are contained inside the interior of the closure over all Fatou components. And since there's more than one Fatou component, and these sets are then disjoint, pairwise disjoint, you know that you cannot cover an entire plane. So the complement of this set on the right is more than just a point. Okay. So the regular open set, this is a necessary condition. Maybe let me just emphasize here that what does this give you? So why this is good for us. So if omega is a regular set, then from topology you can see that the boundary of this set equals to the boundary if you take the closure and the complement and you look at that boundary, which means that you can find a sequence of points from the outside of this domain, which accumulates everywhere on the boundary. And this is a very important property for us, because this will basically make all the magic, this will allow the magic happen. Okay. Now about the other two conditions, namely that omega is bounded and that the complement of the closure is connected, will be needed for the application of a sort of stronger version of a well-known Runge's theorem, which is the following. So suppose we have K compact set, so n compact sets, K1 to Kn, which are pairwise disjoint and their complement is connected. In each of them, you can choose finitely many points and assume that you have a holomorphic function defined on each of these compacts. Then for every epsilon, there exists an entire function which approximates those functions on prescribed compacts. Moreover, you can make sure that this function agrees with the previously defined functions on compacts precisely on those prescribed points that you want, finitely many points. Moreover, you can also make sure that the derivative at those points are the same as the function that you are approximating. That can be generalized, that you can go to any finite finite order of the derivative, but for us, the first derivative is fine. So this approximation theorem, as you can see it here, it was not in this form. It wasn't stated anywhere, but it's well known among people who do approximation theory, since it's a combination of several results obtained by Benke-Stein, Florak, and Royden long ago. But later I found out that a very similar approximation result was also presented by Ermenko and Ljubic, and some of you may know it under the name of main lemma. Okay, the difference there was that they used infinitely many compacts, but in each of compact they only took 1 point. But the proof is basically the same. Okay, so now back to the question about necessity of the conditions. So I do not know whether the condition that the complement of the closure of omega being connected is also necessary. Now this means that I propose a question. If you know the answer, I'll be very happy to hear from you. So is the complement of the closure of a bounded simply connected Fatou component always connected? So think of it as just taking a disk and a smaller disk from the boundary you take out. So can this be a Fatou component? I think for this to be, if such a bad component would exist, then I think it would have to be a wondering anyhow. But I didn't find any argument why this could be the case. Anyhow, if the answer is positive, so hopefully it is, and somebody has the answer, then our result really describes all possible geometries of a bounded simply connected wandering domains.
Excuse me, Luka, you mean yes. For an entire map, yeah. Right? You don't mean for a meromorphic map, you mean for entire functions?
No, for entire function, right?
For entire functions, okay. Okay.
Yes. Okay. Everything what I do here is an entire function. Okay. Yeah, that's it. So let's say something about the proof and the idea behind it, right? So let R be some positive number and Mn be an increasing sequence of integers, such that the disks centered at these integers are pairwise disjoint, and they are disjoint from omega. Now, recall that since omega is a regular open set, we can find the sequence of points from the outside, so outside the closed omega, which accumulate everywhere on the boundary of omega. So the idea is to construct a sequence of entire functions which converges to result, the final entire function with the following properties. So first of all, the nth iterate of omega is contained in one of these, precisely in mth n disk of radius r. The function f has an attracting fixed point somewhere outside omega. So this is the second one. The third thing is that points, that the sequence of points that you have chosen before, that your that your function maps these points eventually onto a attracting fixed point. So basically saying that these points belong to the pre-images of your attracting fixed point. So the first item here, the first property implies that that omega is contained in the Fatou set, because the forward iterates are uniformly bounded. Moreover, they leave every compact set because the sequence is increasing, so they eventually wander to infinity. So omega is contained inside the Fatou set, but a priori it might be contained in some larger Fatou component, right? Now, 2 and 3 then implies that the pre-images of an attracting fixed point accumulate everywhere on the boundary of omega. So therefore, this omega, it has to be a component, not just a part of some component. So it really has to be a Fatou component. And this basically gives you prescribed geometry. So whatever you want, you can get. Okay, and the fourth one is just a part that is also added to the theorem, which it's not needed for this argument here. Okay, so this works in all generality. Now the question is how to construct this sequence of functions Fn, and I will do this next. We'll try to construct the first 3 functions, and I think then you will see the idea how it goes. When you do the inductive process further. And I'll do this simply for a unit disk, because the picture is, I'll try to do a picture proof, so to keep things simple. So what does this picture represent? So in here, the small disk inside here, you can think of it, this is a unit disk, and the outer one is the disk of radius 2. And then you have disks, smaller and smaller disk from the outside. So the closed disks, which whose intersection is a closed unit disk. So this is defined. And we'll call them sets UN, just for simplicity. So this is U0, this is U1, this is U2, and so on. And then you can define a sequence of points which accumulates everywhere on the boundary. Moreover, I mean, you can make sure that, let's say this point here is x1, which is contained inside U0, but outside U1, so in the complement of U1. And this is, let's say, x2, contained inside U1, but outside U2, and so on. Okay. Now, let me try to explain the picture and how we find the first map, F1. So this here inside, so that the dotted circle is your unit disk. So the one that you want on the end to be your wandering component. This here is a disk of radius 2, centered at the origin. This here is the disk of radius 2, centered at 8. Now this here is the shaded disk is a disk of some of radius between 1 and 2, and let's call this set U1. And we know, by the way, how we have chosen the sequences of points and the sets. X1 lives outside U1. Okay, so let's say this is one compact. So this is K1. Then this point, X1, is another compact. And let's say this point 3, which is outside here, is a third compact. On here, we define a holomorphic function, which is translation by 8. On this compact here, we say, okay, let's just be a constant function, which is equal to 3. And on this compact here, on the point 3, you define a linear function which fixes point 3 and has a derivative 1/2. So it makes it an attracting fixed point. And then your then the theorem that we have seen, the approximation theorem, you can find a function f1 which does basically what I just said. So approximates it's so you can find a function f1 which maps this u1 almost as a translation by 8 here, and then you can make sure that it agrees on this compact, on this point of the compact. It's just a point. So it maps x1 to 3, and it maps 3 into 3, and it has a derivative at 3 1/2. Okay. So this part was sort of, it's very important to sort of fix those points where they go. And that's an important part of the approximation theorem that I presented. And that's used very much here. Okay. So what about the second one, the second map? Okay. So now forget about the previous disk. This disk outside here is the U1, previously known U1. And then you go to a slightly smaller disk, U2. So now you know that you have another point here, the one that the part of the sequence that accumulates around the unit disk. Okay. And you can look at it at its image under F1, and it's going to be this point. Let's call it X21. Okay, and then you can also look at the image of this disk here under F1, and it's going to be this disk, or sort of almost a disk here, because the map was almost a translation by 8. Right. So now you can take a larger disk containing all the sort of previous disk and the previous fixed point that you have sort of made before, and then you say, okay, let this be our new compact K1. This is going to be another compact K2, this point, and this is going to be another compact K3. And then you can sort of do it thing again. Here you take a function which is a translation by 8. This point you want to map to an attracting fixed point. And on this larger disk, you want to approximate previous map, right? Because eventually you want maps, these functions to approximate previous ones so that you get a convergent sequence, right? Okay, and you can do that using approximation theorem. So there exists a function f2, which is arbitrarily close on this compact to h3, arbitrarily close to this, to translation by 1 on this set, and maps this one here. Okay, so moreover, you can make sure that it does the same identification as a previous function. So you can make sure that f2 maps x1 to the same point as f1 maps x1. You can make sure that x2 is mapped to the same point by f2 as it is by f1, and this means to this point. So what I'm trying to say here that is, once you have made some kind of orbit, you wish to sort of keep it. You want to keep that information. So for instance, okay. Furthermore, you want to keep this point to be an attractive fixed point, which you can do, and you want to map this exactly here. Okay. And the third one, you can sort of have a similar picture. So you go again, take a smaller disk, then you have another point here, then this point. So once you have F2, you can find this point. So I mean, this point is already given, but this is its image under F2. This is its image after the second iterate of F2. So this is a U3, so it's another compact, smaller disk. This is its image, and this is its image under the second iterate. Okay, and then again, you say this is a compact on which you want your map, a new map, to be a translation by 8. This point of the orbit you want to sort of map back to an attracting fixed point. And on this large disk, the yellow one, you wish to approximate previous map. Okay, and then again, the same argument goes. Yes, you can do it by the approximation theorem. So you can find a function which agrees with the previous function on all the previously defined points. So this means that x1, x2, x3, x31, x21, on all these points, the new map F3 can do the same stuff as F2. Okay, so why we can do that is because we only have finitely many points. So if there's an infinitely many points, then you cannot do that. Okay, and I hope now that you get sort of idea how the inductive procedure can be continued on. I mean, next time you take an even smaller disk and then another point from the sequence, and eventually it's going to get mapped into a fixed point here. Okay. So this is an escaping case. What about the oscillating one? I will not do the proof, but I will just show you this picture, how in the oscillating case, the thing looks like. So now, if you want to have a unit disk as an oscillating wandering domain, it's for the proof. It's easier to think about. It's easier to do the proof if you think that you'd have some small that your disk that you're trying to make a wandering. It's some smaller disk which is outside the unit disk. You can do this by linear change of coordinates, and just think of it that your disk that you're trying to make a wandering domain is the black one in here, and then this shaded disks outside are just the sets U1, U2, and U3, and these points that are let's say here, these points that are drawn here are just the points from the sequence that accumulates everywhere around. So these are just the first 3 points. And then the dynamics is basically like this. So you map inside let's say some disk of radius 1/2. And then on that disk, you define a map, which is a translation by 4. And before you map this guy here inside here by, let's say, a linear function or approximation of it, you make sure that this point x1 is mapped onto, let's say, one which you previously make to be a attracting fixed point. And then the procedure is basically very similar. So the dynamics is basically like this: is a translation by 4, then you map it back to this disk, then it's a translation by 4, translation by 4, and goes back, and so on. Okay, so from here you can see that also from the previous case, we are just making translations on the unit disk. So if you do approximation very well, I mean, if it's sufficiently close, then you can make sure that all these iterates stay univalent. Now, if somebody might wonder, what can we say about this wandering domain in terms of classification? You can make sure that it's how it's called, bounded away from the boundary type, so the orbits inside the disk don't converge to the boundary. And since the map is the forward orbit is univalent, it's eventually isometric type one. But there's some freedom in this construction. So namely, if you see the function that we are using here, let's say this H1 that it's a translation, you could replace this by something. I wouldn't go into details, but there's some freedom in this construction that if somebody wants to play around to do something else, it may be possible. Okay, how much time do we have? Okay, much. So maybe just to say something similar, I can say something similar in higher dimension as well. So for those that are not familiar with with the notion of polynomial convexity, I will just give a definition, and I mean, hopefully you understand it. Otherwise, I mean, it's not a big deal. So the polynomially convex hull of a compact set inside Cm is defined as a set of all points in a complex Euclidean space, such that the modulus of P of Z is less or equal to the supremum of P over this compact set for all polynomials P. So we say that a compact set is polynomially convex if its polynomial hull is equal to K. So, and this definition is well defined as well as in dimension 1, and there we have the following nice representation. So the compact set K is polynomially convex if and only if its complement is connected, right? So unfortunately, we don't have this nice connection in higher dimensions, but at least in dimension 1, this is something that you are probably more, it's easier to understand what means that the complement of compact set is not connected than this abstract definition. Okay, so in higher dimensions, I have the following very similar result, which states that if omega is a bounded regular open set whose closure is polynomially convex, then there exists an automorphism with an escaping or oscillating wandering domain equal to omega. So you can see that if you replace this, if you assume that this M is 1, and if you replace the word automorphism with the entire function, and this is precisely the same statement as we had before. And funny fact is that this I proved this theorem a year before I realized that, I mean, the easier version could be made as well for entire functions. So usually it goes the other way around, right? From dimension 1 to higher dimensions, then from higher to lower. So somebody may wonder what are examples of these types of domains that satisfies these conditions in higher dimensions. So let me just give you a few examples. Any bounded convex domain in Cn is of such type. Now, topologically non-trivial examples would be the following. So take any totally real compact manifold of dimension less than n. So if you don't know what totally real means, you can just think of it as a compact real manifold inside Rn. And then you can think this Rn is canonically embedded inside Cn. So take any such manifold, totally real, you can perturb it slightly, such that the new resulting manifold is still totally real, compact manifold, which is now polynomially convex. And in particular, it has the same topology as the manifold that you started with. Then you can take appropriate tubular neighborhood of this M prime, and then you obtain a set which satisfies the conditions. So think of it, let's say in the case of 2 dimensions, let's say in C2, inside R2, the condition is that you look at the real compact manifold of dimension 1, which is then just a circle, and then you just take a neighborhood of this circle inside Cn. Okay, so this will be a topological interpretation, right? Okay, and just a few words about the differences in the proof. Of course, I will not talk about the proof in the details, but just say that the proof is essentially the same. So you have your set, open set, and take a closure, and outside you take a countable set which accumulates everywhere on the boundary, and you wish to find a function or an automorphism in this case, such that the iterates of this map are normal for monomer family on your domain, but all those points that you have chosen belong to different Fatou components. But then clearly the proof is a bit more complex due to the restrictive nature of automorphisms, because you have to make sure that your map is injective. So those points are not mapped to a single fixed point, attracting fixed point, but for each point they are mapped to a different attracting in the region of some attracting fixed point. So not on to it, but in some small neighborhood of it that you can make sure that it gets attracted. Another trouble which you don't have in dimension one is the following. So if you remember that the way how the construction was done, that it was like we constructed a sequence of entire functions which converges in the end to entire function with nice properties. Now here, if you have a sequence of automorphisms, there is no guarantee a priori that the limit map is going to be an automorphism. I mean, you can make sure that it's going to be injective, but it's very likely that you will lose surjectivity. And there's some tricks that you need to use that you can make sure that the map is going to be surjective as well in the end. Okay, and then finally, the key ingredient in the proof is as before, some approximation theorem, and in this case is the approximation result of Anderson-Lempert theory for automorphisms, which is slightly more restrictive, but basically does the same. So you have n compact sets, k1 to kn, which are pairwise disjoint, and such that all but one are star-shaped. If you don't know what star-shaped means, you just think of it as a convex set, let's say, simplicity. Convex sets are of this type. Now, assume that you have n automorphisms fj, and that such that the images, let's say, k prime j is the image of fj of kj, and that these images are disjoint. I mean, otherwise there's no automorphism which would do something like that if the images would be not the images would intersect. Okay, so if the sets A, which is the union of all compact sets, and B, which is the union of all images of these compact sets, are polynomial convex, then for every epsilon you can find an entire function which approximates the given automorphisms on prescribed compact sets up to epsilon. And in particular, you can make sure that G can be chosen so that the infinite order jets agree with corresponding jets of F of the automorphisms Fj at any finite given points inside Kj. Okay. Right. And what maybe, okay, I have 2 more minutes, maybe I can just say one more word. So the particularly more problematic part here is to prove the oscillating case. So the escaping wandering domain is easy to produce, or easier. The oscillating one needs to be done slightly differently, because you cannot sort of take your compact set and move it back close to the origin, because there you have already defined something and your map is automorphism, and there's no way that you can do this with the injective map. So the idea is that you start with the map, and you start with a map which has a saddle fixed point at the origin, and also all the functions that you construct or automorphism that you construct later, they will all have a saddle fixed point at the origin. So what this means is that if you have such a fixed point, then you have a stable and unstable manifold, right? And suppose you have a compact somewhere outside, far outside. How can you get an oscillation? Is that you take this compact set, you move it close to the stable manifold, close enough, and then the property of a stable manifold somehow gives you the desired property, which means that if you take iterates of the set now, it will be close to the stable manifolds, and will get close to the origin, and then it will get close to an unstable manifold, and then it will go out some compactors again. And this is how you sort of produce the oscillation in that case. And I think I will stop here.